In this video, we'll talk about the last possible option for eigenvalues in the case of a matrix, and those are repeated eigenvalues. And just like repeated roots were a problem before for second order equations, repeated eigenvalues are a significant problem. So we have two matrices here. We have 3, 0, 0, 3 and 4, 1, minus 1, 2. We can look for the eigenvalues and eigenvectors of these matrices. So in the first case, we see that determinant of A minus lambda I is going to be the determinant of 3 minus lambda, 0, 0, 3 minus lambda. So when I expand that out, I just get 3 minus lambda squared equals 0, or a double root at 3. But then the matrix A minus lambda I that I go to solve the system for to find the eigenvectors is just all zeros, which means I can pick any vector as an eigenvector here. Every single vector is an eigenvector of eigenvalue 3. So in particular, I can pick two of them that are independent. I can pick v1 to be the vector 1, 0, so the standard basis vectors, and v2, v0, 1. And I get two linearly independent eigenvectors. And so I still get a basis for R2 out of these vectors. Now, in the second case, we'll see that's not quite the situation. So for 4, 1, minus 1, 2, I do the determinant again. It's the matrix I get is 4 minus lambda, 1 minus 1, 2 minus lambda. I find the determinant, 4 minus lambda times 2 minus lambda plus 1. This will come out to be lambda squared minus 6 lambda plus 9, or again, lambda minus 3 squared. So I still get my double root at 3. But when I go to solve for the eigenvectors, the matrix becomes 1, 1, minus 1, minus 1, which means I only get a single vector at 1, minus 1. So I only see here one linearly independent eigenvector. I can't get a second one. I could double this to get another vector, but it's not linearly independent. So for these two different cases, we see two different problems here. We see one problem where I still get a basis of R2 from the eigenvectors, and the second one where I don't. That second one here is the issue. This is sort of like the situation for repeated roots where I didn't have enough solutions with just the one that I had. I had to find a second one somewhere. The same thing sort of happening here. I only have one eigenvector, and we'll sort of address this later on, what you do with it. But it's an issue to be addressed. Let's define some things here to talk about what's going on here. So this lacking case here on the right was more concerning. So we define some terms here. The algebraic multiplicity of an eigenvalue. So we have a square matrix with R being an eigenvalue. The algebraic multiplicity of R is the power of the factor lambda minus R in the characteristic polynomial of the matrix. And the geometric multiplicity of R is the number of linearly independent eigenvectors I get for eigenvalue R. So from the last example, for that first matrix, 3, 0, 0, 3, we had that the algebraic multiplicity, or the power of lambda minus R, was 2. It was lambda minus 3 squared, so 2. And there were two linearly independent eigenvectors. For the second case, with algebraic multiplicity 2 as well, it was still lambda minus 3 squared, but there was only one linearly independent eigenvector. So we say that an eigenvalue is defective if this geometric multiplicity is strictly less than the algebraic multiplicity. So what it really means is I don't have quite enough eigenvectors. The power in the equation of the algebraic multiplicity tells me how many I would expect to have. I should expect to have 2. But the geometric multiplicity is how many I actually get. And so in that case, I got 1, which means I don't have enough. So a theoretical result in this area says that for any eigenvalue, the geometric multiplicity is no bigger than the algebraic multiplicity. And for an eigenvalue, the geometric is at least 1. Right? This bottom thing here is the fact that if I have an eigenvalue, it has to have at least one eigenvector. So this here is at least one eigenvector. This here is a property of how matrices work, which is why we didn't have any problem when we had distinct roots. For distinct roots, this multiplicity is 1, which means if this is 1 and this is 1, this must also be 1. Everything matches and we're happy. The issue is when this here is a strict inequality, then this is deficient or defective. If it's not equals, but it's strictly less, that's a problem. How do we deal with this? I mean, at this point, there's a way to deal with it, but we're going to kind of ignore it for now. So there are these things called generalized eigenvectors. And the idea of them is the fact that I am missing eigenvectors. I need to find more vectors to get me to something that works. Because I want to get to this basis of Rn from the eigenvectors. That's really the gold standard we're aiming for, is a basis for Rn from the vectors. But I'm short. If I have a defective eigenvalue, I am missing enough vectors to add up to n. And while these generalized eigenvectors don't do the exact same thing as normal eigenvectors, they're sort of close enough to sort of fill out what we need. But the easiest way to think about what these are, what they're doing, is in the context of solving differential equations. So we're going to hold off on what these are and how they work until we get to them sort of arising more naturally in solutions differential equations. They're very cool things of their own right, but in terms of actually progressing things forward, the easiest way to define them and bring them up is when we need them later. So they'll come back up later. We'll see when they show up and what they do. I'll give it a hit, we're multiplying by t again, and things are going to work out, but we'll see it at that point. That's the idea of repeated eigenvalues and where they sort of cause issues. We're not dealing too much with them yet. The point here is just to know that this exists, and it can cause problems with getting to this basis for Rn that we want. And we'll see more about how to fix this problem. We actually try to address it in the context of solving differential equations in the next chapter.